Good afternoon, everyone, and welcome to yet another intriguing session of Book Code Summit. In this session, we have our special guest, Miss Anna Veronica Dorogush, all the way from Moscow, Russia. Anna is the head of machine learning systems at Yandex and also a judge in the WooCode hackathon. She is also the head of CadBoost. Today, she will be hosting what I believe will be an insightful workshop on solving classification problems with CadBoost. So, with this, I would like to welcome Anna in the panel with me.
Hi, thank you so much. I'm actually not working on CadBoost right now. I am the person who has created the library, but I am now doing self-driving cars.
Okay.
But it's still great to talk about this library. So yeah, today I think in the schedule there was something about finance. I do not have anything to do with finance. It will be a talk about machine learning.
All right.
We are going to talk about machine learning, specifically about gradient boosting and specifically about CadBoost. So what is CadBoost? CadBoost is an open source library. Open source means that it's available for free to everyone. It's on GitHub, and you can install it using pip install, which we will do a little bit later altogether. The library has 6.3 thousand stars, so it's pretty popular. Also, the library is used by a lot of people. According to Kaggle review of 2021, so last year, it's the seventh most used framework in the world by machine learning and data scientists. And you probably know what is Kaggle. It's a platform where they have a lot of machine learning competitions, the biggest one in the world. So this data is, I would rely on this data. What problems does CadBoost solve? CadBoost solves supervised learning. That means it solves the following kinds of problems. You have some data, some historical data. For example, in finance, you want to work with credit scoring. You have some data about people in the past, if they have paid the credit or not. And what you want to do, you want to predict in the future, are they going to pay the credit or not? Is it some new person? Is the person going to pay the credit or not? So there is some application and some problem that you want to solve. You have data at hand, and for this data you have answers, correct answers, and you want to build a model that would do predictions for some new data that you have not seen before. For that, there's a bunch of tools that are available for everyone. There are linear models, neural networks, decision trees, and many others. So there is a bunch of these algorithms, and it's important to understand which ones you should use. The simplest rule that I will give you now, and this rule is actually used everywhere in production, is the following. If you have unstructured data, for example, you have music, DNA, images, videos, something like that, then you give it to a neural network and you train a neural network. That's the first type of the data. The second type would be tabular data. For example, for prediction if a person will like a song or not, you have a tabular data. Every person is described with a set of features, like every person and person plus the song. There would be some features that are describing the person, some features that are describing the song, and it will be like a table of numbers. It might be a table of numbers, but also it's allowed to have non-numerical values. For example, for if you are doing credit scoring and you have features of a person, one of them could be occupation, which is not a number, it's a category, but it's also allowed. So for tabular data, you normally use random forest or gradient boosted decision trees. Usually gradient boosting works the best. For that reason, for example, in the same Kaggle, the competitions with tabular data have a lot of solutions that are based on gradient boosting. So a couple of words about gradient boosting. First of all, it is currently the best solution that you might have for heterogeneous data, I mean tabular data. Secondly, it's very easy to use. We will use gradient boosting and build a gradient boosting model in a couple of minutes. And that is a little bit opposed to neural networks, because for neural networks, you really need to be an expert to use them. To get a good model, you need to know what you are doing. In gradient boosting, you don't really have to know what you are doing. It's really very easy. It's just a call of one function, more or less. And the third thing about gradient boosting is that it works super good even if you have small amounts of data. So you do not have to have huge amounts of data that you need to have for neural networks. What are the current applications of gradient boosting? Basically, it's used everywhere. Gradient boosting is used in search engines, in weather predictions, in sales predictions, everywhere, in finance, in medicine, in many places. All the big tech companies use gradient boosting for their machine learning. And not only them, but also research uses gradient boosting a lot. So you might find many papers where people are trying to do stuff with gradient boosting. For example, in CERN, in a big Hadron collider, they use gradient boosting, in particular CadBoost, for classification of the particles. So it's heavily used in research, and it's also heavily used in machine learning competitions. Again, because it's very efficient, very easy to use, it gives you good results. So what exactly is gradient boosting? Gradient boosting is an ensemble of decision trees. A decision tree is a very simple structure. Let's say you have some object that is described with several features. For example, this object would have a feature if it is an animal, if it has whiskers, and if it purrs. So now you want to build a decision tree from that. What you do is you ask questions, and these questions must have a yes or no answer. For a number, it would be like the height is greater or less than 150 centimeters. Yes or no. For binary features, it would be yes or no. Is it an animal or no? From that, you build a tree. Is it an animal? Yes. Does it have whiskers? Yes. Does it purr? Yes. And then you go to a leaf. Leaf values, if it is a single decision tree, then leaf values can have answers in them. Then you can just use a single decision tree as your machine learning model. But normally in gradient boosting and also in random forest, you use more than one decision tree. And to do that, you need numbers in the leaves. So there will be this structure for a decision tree, and the leaves of the tree, so this last nodes, will have some numbers. In gradient boosting, you are building a sum of these trees. So you build the first tree, and you have some value of your loss function. So your model has some value of the metric that shows how good is the model. Then you add to this tree another tree, and the summation works as following. The first, your object falls in some leaf of a tree. In this leaf, you have some number, and you add this number to the result. Then you look on the second tree, and in the second tree, the object falls into another leaf, and there is another number. And the sum of these leaf values, where this object falls, that is the result of the sum of the trees. And you do this normally for hundreds or thousands of times. You sum these new trees, you add new trees to the ensemble until you have your loss function is very small. And this big ensemble, this big sum of the trees will be your resulting model. There are three most popular gradient boosting libraries in the world. The first one to put in open source was XGBoost. The second one was LightGBM. The latest one was CadBoost. All three libraries are in top 7 most popular machine learning frameworks in the world. And I think it's important if you plan to do something with machine learning and with data analysis, you have to learn all of them, as well as all the other, so all the top 7 instruments that Kaggle says are the most popular in machine learning. They're sklearn, TensorFlow, PyTorch, this one. So you probably should try all of them. There are some differences between these three gradient boosting libraries. They work with different types of data. All three of them are able to work with numerical data. So that means that all your features are numbers. For example, for credit scoring, it could be the value of your salary. But there are also other types of data in the world, for example, categorical data, and XGBoost is not able to work with categorical data. LightGBM does not work really well with categorical data, and CadBoost works with categorical data pretty well. So if you have a categorical feature, you should probably try that. Try this library. It's also possible to work with text features. That means that you might have an object that is described with some numbers, some categories, and some text features. What you do, you collect this as a table, where each line in the table is an object. For every column, you know the type of this column. So you are saying this is a numerical feature, this is a categorical feature, this is a text feature. And then you just give it to the model, you train it, and you are able to make predictions. What are CadBoost advantages over other gradient boosting libraries? There are several of them. First of all, CadBoost gives good quality with default parameters. What does this mean? This means that you do not have to tune parameters a lot. Actually, from the first run, without changing anything, you will already get a very good model. As opposed to other libraries where you really need to tune parameters to get a good model. So you need to try different ones, compare them, and see what works best. The second thing is the following. The speed of the training on GPU of CadBoost is very, very good. So it's super fast on GPU. And it also makes very fast predictions, which is important if you do production. But normally people, if you are a student, you normally don't care about production, you care more about machine learning competitions. So here, if you have access to GPU, then it would work very, very fast. The next thing about CadBoost is that it has sophisticated categorical and text feature support. And I told you about that CadBoost supports different types of data. It also has a bunch of ways to analyze the model, to analyze the features, to understand what exactly the model does, and to understand your data better. That's about advantages of CadBoost. And here are some resources where you can read about CadBoost. There is a website, CadBoost AI. There is a GitHub page. And on GitHub page, you can make an issue, or you can contribute. It would be also very, very nice if you would do so. There's a bunch of issues to contribute. And there is a Twitter account where you can read the news, like where is the new release and something like that. With that, we will start our practical part. And to start the practical part, you need to download the notebook. We will be running the notebook together. Here is the link, so please do that. do that first, and then you will have to install several libraries that are listed on this slide. And you need to run this command to enable visualization in the browser. I will give you a couple of minutes to do that. And in the meantime, I will open my notebook in the browser. So what you do is you are downloading the notebook. It's in IPYNB format. Then you open your console. You go to the folder where this notebook is downloaded, and you run Jupyter Notebook there, so that you are able to open the notebook and to run it. The slide is here, so please do the steps. And I wait a little bit to make sure that you have done this. If you have not done it yet, please make a screenshot of your monitor to download it while we are starting. And I will be sharing the next window where I have started my notebook, which has the same data that that you are going to download. Okay. Time for a screenshot. And I am stopping to share this particular screen. Did you download something? It would be very nice if I would be able to understand if there was enough time to download for everyone. Okay. I hope you did. Then we will be doing the tutorial. Good. Now that will be a tutorial that will show you that is a simple example of how you are running CadBoost on a data set. Basically, it's very easy. You can do it with CadBoost. You also can do it with other gradient boosting libraries, and I strongly suggest you to try all of them. They work a little bit differently, and it's also nice if you are solving a machine learning classification to try all three of them and probably do some stacking, or just select the one that works the best. They work similar. So let's start. We are going to solve with you a classification problem. Classification problem is a problem where you have some data, and for every example of the data, we are solving binary classification. So you have an answer, yes or no answer. Or the label that will be 0 or 1. The answer that you are trying to predict is 0 or 1. We are going to work with some Kaggle challenge. It's Amazon Employee Access Challenge, which has the data set where you are trying to predict if an employee will be granted access to some role or not. That is a link to the competition. Here is a list of libraries to install. You can uncomment these lines if you have not yet installed the libraries that I have shown you in the presentation. So please do that. and we will follow the next steps. First, let's check what is the version of the Python that we have and the version of CadBoost. That is the latest version of CadBoost on GitHub. It's 1.0.4. And let's start reading the data. CadBoost library has a sub-library of datasets. It has a few datasets that allow you to play with CadBoost with different modes and discover different features of the library. We are downloading Amazon dataset here. Let's take a look on what we have in this dataset. In there, we have several columns. The first one is called action, and that is the column that we are going to be predicting. Other columns are called resource, manager ID, and some other features. First of all, let's select the label. We will be building X matrix and Y column. Y column will be having label values, and X matrix will be having the feature values. And that's what we do here. We select by name, we select a column for labels, and then for the result, we remove this column and put the data without this column to our X variable. Let's look a little bit on the features. The features are like manager ID. This feature has some weird values. It's like 14457 or 1540. If we will be trying to work with this feature like a numerical feature, where we are comparing these numbers, which one is greater, which one is less, and when we are relying on the order of these numbers, it probably will not work well. And it will not work well, yeah. So what we want to do, we want to make sure that we work with this feature like a categorical variable. A categorical variable is a variable that has some fixed set of values, which are not necessarily comparable with each other by greater or less. If we look on other features, they all seem to be like that. They all look like some hashes. So what we are doing, we are declaring all these features as categorical. What you need to do to declare that, you just need to make a list of indices of these features. It's also allowed to make a list of names of the features. So you could make a list of manager ID, roll up 1, roll up 2, and so on. But here I am just using the indices. Now we have a list of indices of categorical features in our dataset. Let's do another small thing that we always should do when we are solving classification problems. We are solving binary classification. The labels are zeros and ones. So it's usually good to look on balance of the classes to see what labels we have and how many of them we have. We can see that in the whole dataset, we have only 2 labels, 0 and 1, and we have small number of zeros and big number of ones. That means that our dataset is imbalanced. It's good to know things like that. Now, what we can do, we can work with the dataset like X and Y. So just use X and Y. It's a possibility. But we also can create an object that is called pool and work with the pool object. The pool object has a bunch of syntactic sugar. It's also efficient in terms of speed, but that's probably not the detail that you have to know when you are using a library for the first time. So basically, it has a lot of syntactic sugar. For example, you have the function get feature names here. So one option to work with a data set is to create a pool object. We have read our data, we have understood something about it, that the features are categorical, that the balance of classes is off, so it's unbalanced. Now we are ready to train our first model. How do we train the model? When we are doing machine learning, we always split our data into train and validation. The training data will be the data that the model is trained on, and the validation data is a smaller part of the data which shows you that your model does not overfit, so that your model will be good for new data that you have never seen before. A pretty normal size of the for a small data set, a pretty normal amount of the data for validation is 20%. So here I am setting train size to 0.8, and the rest will be put to validation. We are ready to train our first model. If we are not specifying anything, if we do like that, then we will get already a good model. But what I want to do, I want to specify the iterations parameter. What is this parameter? This parameter is the number of trees in the ensemble. I have shown you in the slides that gradient boosting builds an ensemble of many, many trees. By default, in CadBoost, it's 1000. But it takes a while to train a big model with 1000 trees. And I want to show you something very fast. So I will train a model with only 5 trees, which will not be a good model, but it will be a good example. That is how you create a model, and that is how you fit a model. What you specify here? You need to specify X and Y. Those are the metrics with the features and the vector with the answers that you know. You also have to specify non-numerical features. So there is a parameter called cat features, and here you need to put the list of features which you consider categorical. If you by any chance have text features, then there is a parameter called text features. By default, all the features are numerical. So if you do not specify cat features, you will get a model which thinks that all the features are numerical. So you need to specify, to train the model, you need to specify X and Y for training, and you need also to specify X and Y for validation. I don't want to look on the standard output, so I'm setting verbose to false. I'm fitting the model, and now I can take a look on the model, what I have. I am printing if the model is fitted, and I am printing the parameters that I have set in the model. And the model is fitted true because I have run the fit function. And the model parameters that I have specified are iterations equals 5. I have not specified anything else. Okay, we have trained our first model. Now, after that, you are able to train a gradient boosting model, and that is almost the best thing that you can do with if you have like any data set. Just don't specify this thing, and you will get very, very good model. Okay, now let's take a little bit deeper dive into what you can do and how it works. If I do not specify, here I have specified verbose equals to false. If I do not specify that, then I am able to look on the standard output of the library. What I can see here. First of all, there is a learning rate parameter, which is set automatically based on number of iterations and based on the parameters that you have, and based on the data set also. You might specify learning rate, but by default, it's calculated automatically. There is a machine learning model that selects a good learning rate for you. Then for every iteration, for every new tree, you have several lines. Every line says how many trees have we trained before, what is the training loss, what is the validation loss, and also what is the best validation loss that you have got so far. Here we train a very small ensemble, so the very best validation loss that we have got is the same that we have got on the last iteration, and that is the number of the best iteration here. But if you would train a bigger ensemble, then this loss would decrease, and at some point it would start increasing again. So for some iteration, for a big model, if you have like 2000 iterations, then first 1000, the loss will be decreasing, this validation loss, and then it starts increasing. And then you have here this number of your best iteration, or best number of trees that you have used. Also, you can see how much time has passed since you have started the training. And you can see that your training is working like 5 hours and it is still not done. But the very nice thing is that you also can see how much time has left. So how much more you have to wait. Normally, if you are training for thousands of iterations, you do not really care about all this standard output. So you normally want to look on it every now and then, every some number of iterations. Here I set it to 5. So here we are looking on every 5th iteration. In the end, you see the best error that you got, and you also see the number of the iteration where you achieved these metric values. That is the standard output, and if you are training in the console, then you normally look on that. But you are also able to train in Jupyter Notebook, and that is exactly what we are doing right now. There is a parameter called plot, which allows you to plot some graphs. So you are able to look on the validation metric and on training metric here in Jupyter Notebook. The dotted line is the training error, and the full green line is the validation error. We are normally looking on our training loss, and by default, that is something that you have in your standard output. That is log loss. That is something you can specify here. So you can specify as a parameter the loss function that you want to optimize. For binary classification, it's normally log loss. But sometimes you care about other metrics also. You are optimizing log loss, but let's say you care a lot about other metrics, for example, AUC or accuracy. If you care about them, you might as well plot them. And here they are. There are several tabs where you can look on the metric graphs for AUC and for accuracy. The full green line shows you the validation metric. For AUC, CadBoost does not calculate the value of the metric on train because it's very computationally expensive, but there is a parameter to calculate that if you want. Normally you don't want that. Normally you just care about the validation. You normally just care about the validation metric. What else can you see on this graph? Here you can see how much time has left and how much time has passed. After the training is finished, you only see how much time has passed, so it's time spent. But during the training, you can also see here how much time you need to wait. So you do not have to look on the standard output to see this remaining time. You are also able to see this here in the visualization. What else? There is a dot here. And the dot on every metric. On every metric, there is a dot. What is this dot? That is the iteration or the number of trees where you got your very best metric value. Normally, like for AUC, the validation metric will grow, and then it will start to decrease. So you need to specify this moment where you have the best model. Because we are training here for a very small number of iterations, even though we automatically are setting a big learning rate, it's still not overfitting. So the best model is in the end. The next thing is that we are able to compare several models. There is an important parameter, one of the most important parameters in gradient boosting that you should play with, and this parameter is called learning rate. The smaller is the learning rate, the later you will be overfitting, and the more trees you need. So small learning rate means you need a lot of trees. Big learning rate means you need small number of trees and you will overfit. Normally, if you are able to have a lot of trees, you are willing to wait, and you have all the computation time that you need when doing the predictions. Then it's better to use many trees for your model. But to use many trees, you will have to use a very small learning rate. We will be here comparing two models. One has a very big learning rate. Another has a smaller learning rate. We are creating these two models, model 1 and model 2, and we are fitting them. We are fitting it the same data and the same validation. And of course, the same categorical features are specified. So let's train them. We still are training a small ensemble of 100 iterations, which is a demo mode. Normally you train bigger models. Normally you do not want to train just 100 trees. It's too small for a good model. But what I want to show you, how you can compare those models. To compare those models, you call metric visualizer. You specify the folders here where you are storing the data. It's you use a parameter to do that, and you compare the models. So which model has a big learning rate? Which model has small learning rate? This one has big learning rate, so it is doing very big steps to decrease the error. But it overfits here. So you see the blue dot is way before 100 iterations. And the one with small learning rate has the green dot in the end. And if you would train it much longer, most probably, or there is a big chance that this model in the end would be better than the second one. Okay. The next thing you have to know is that the model overfits at some point. So the loss value, the best loss value is not the last normally. So it's not the last iteration. And by default, CadBoost cuts the model by the best iteration. So let's say you are training this model and your best iteration, you're training 100 trees, iterations equals 100, and you set a learning rate to 0.5, which is a very big value, which you should not use in production. Learning rate should be smaller, but that is a demo mode. And when you train such a model, you overfit after 80 iterations. So let's see how many trees has the resulting model. It has 82 trees. So it has thrown away all the rest. It throws it away automatically. You don't have to throw it away by yourself. The model does it. The code does it for you. The next thing, sometimes when you're training a model, what happens is if you are training on the model on one part of the data, you have then the error has one value, and when you are training on another part of the data, then the error is very much different, and it can happen. And you want to understand this, so because you want to understand. You want to, for example, if you want to select the best parameters for the model, and you are comparing several models, what you want is you want to understand which is this different in metrics significant or not, or is it because of some noise? And to understand that, you can split your data into several parts and do cross-validation. So, for example, here we are doing 5-fold cross-validation. And as you can see, the graphs for validation losses for each of the folds, they are very much different. So there is a lot of noise, and that results in a big difference in resulting validation values. And what you want to look on, you want to look on the mean value and on the standard deviation of the validation loss. This helps you understand what is what would be the average validation loss for your model on cross-validation. The next thing that you should know is called snapshotting. So let's say I am training a model, and the model has 100 trees, or let's say it has 5,000 trees, and it trains for a day, for a whole day. What can happen? What can happen is that your computer goes to sleep, or something else happens. I don't know, something, and everything is lost. You don't want everything to be lost. And for that reason, you normally save every iteration, or every several iterations, or every several minutes, or something like that. You save your resulting model to the snapshot. That is something that you do in neural networks also, because they also train for a long time. Now, if you have the snapshot file, and you have trained the model, you are training one more time, then no work is done. So it instantly gives you an answer. Let's try removing the snapshot again. So we are training this now. Let's set it to 1,000 iterations. So we are setting it to 1,000 iterations and training. And now I do stop the kernel. Let's see, the kernel has stopped after 69 iterations. Okay. Let's train again. So what you can see here, it starts from 57th iteration. So everything else it has saved to the snapshot. Okay. Let's stop it again and train for 10 iterations to make it faster. Oh. Yeah. Okay. That's about snapshotting. You definitely should use it. And now let's try to make predictions. Making predictions is easy. To do that, you call model.predict. But what you need to know that for a binary classification, model predict gives you a binary answer, 0 or 1, based on the value of probability, if it is greater or less than 0.5. And sometimes you, instead of that, you want to be smarter, and you just want to look on the probabilities. For example, you want to rank, if you want to predict which, to make a playlist, then instead of having 0 and 1 answers, if the user will like or not like the song, you want to look on some numbers here. So which song is more it is which song will get is more probable to get like from a user. Normally, what else you can do? You can train a big model. You can also do it without validation, and then you can validate it on a new data set. Or let's say you have like you are training something and you want to validate it. You have an old model, you have a new data set, and you want to validate it on this new data set. So what you can do, you can call a function that is called eval metrics, and you can see on this new data set, it's called pool1. I have created it before. On this new data set, what would be the metric value on every iteration? You can also plot that. You can look on different metrics here. You do not have to calculate the metric every iteration. You can calculate it every 10th iteration, something like that. Okay. The next important thing is feature importance. So it's really important thing because sometimes you have a lot of features and you don't really know which ones you should use. Some of them are trash. Some of them are good ones. To select good features, you train a model and then you see the feature importances. For this particular model, you can see that the most important feature is the resource and the least important is this one. So maybe you can try throwing it away. And it's good knowledge that you know what are the top important features. But sometimes it's not enough for you to just know which features are important. Sometimes you want to know for a particular example which features are important for this particular example. What we are doing here is we are selecting one line from the dataset. And for this line in the dataset, there are some predictions. The average value on the whole dataset is here. And for this particular example, the answer is way bigger. So it has an answer higher than the average answer. This plot helps you to understand because of which features this answer is so high. And you can see that this feature that is called role department gave it such a big leap to the right. The next feature, roll up, gave it the shift of this size and so on. So it was initially in this base value. Then because of this feature, it came a little bit to the right. Because of this, it came more to the right and so on. And also because of this feature, it went a little bit to the left. And in the end, you got this value. The same thing you can look on another object which has a very low answer, so a very low prediction. There is the same average value, and the value of this particular data example is very low. So you can see that it was here initially, and the average is here, but because of the resource value of the feature that is called resource, we make a huge leap to the left. Okay, and for all other features, you know the size of the leap, so the size of the importance of this feature for this particular sample in the dataset. There is also a summary plot where for each feature, for every feature, you can understand that how this particular feature impacts the points in the dataset. Every point, every example in the dataset, is 1 point. Here is the base value. So the resource, for many objects, many dots here, the feature that is called resource has a small positive value. You don't have to look on the color right now. The color doesn't mean anything here. But yeah, so for the resource, many dots, for many samples in the data set, the resource feature has a small positive influence. And for some of the examples in the data set, resource has a very negative influence on the resulting prediction. And that is the most important feature in the data set. And for other features are less and less important. For example, the roll-up one, for most of the features, it has zero influence on the resulting answer. But for some of the examples in the dataset, it has some negative effect on the resulting answer. So it makes the answer close to zero than to one. And one more thing that I want to tell you is about hyperparameter tuning. I will not tell you about all the hyperparameters. There is a bunch of them, and I strongly suggest you to read some tutorial about hyperparameter tuning later if you will work with CadBoost or play with CadBoost. But the most important ones that you have to know are the number of trees, which by default is 1000, which is a very good default. So it's for many data sets, it's really good. You don't have to change it. But you can. So more trees would not hurt. But you don't really want to set it to. So I will write it like that. It's better to set it to some big value. And you should play with the learning rate. By default, there is some learning rate. This learning rate is calculated automatically using a machine learning model when you start the training, but it's always not the best one. You always can do better. So if you see that your model with the default learning rate, your model overfits fast, then you should decrease the learning rate. If you see that your best iteration, your best validation iteration is the last one, then you should increase the learning rate. And that's the rule of thumb. So with those two things, you always have to play. But there are some other things that you should consider. For example, there is a parameter max CTR complexity, and that's just a parameter for categorical features. You set it to a bigger value, like to 3 or 4, you get good quality, but slow training. You set it to 1, you have not so good quality, but very fast training. With that, we can train a little bit here. That will be training for a while because we are training for 1,500 iterations. I have not passed a validation data set here, so there is only trained data set. And for that reason, you only see this dotted line. Okay, it has already finished. It's still it's really fast, even for 1,500 iterations. But it's because the data set is not huge. And you might as well train on a huge data set. Yeah, with that, I will stop sharing.
Yeah, thank you for that workshop, Anna. That was really insightful. And so, can we go for some Q&As if you don't mind?
Yeah, sure. Let me find the window with. Sorry. Yes, I'm completely fine. Yeah, sure. Let's start the Q&A.
Okay. So yeah, we have some questions. How to select best machine learning algorithm if we have little time to find the best algorithm, like
yeah, that is exactly
ML,
what I told you on one of the slides. there is a very simple rule of thumb. Let me share it one more time. Where is the window with? Sorry. Okay, I don't see it, but anyway, so there is a simple rule of thumb that you should apply. If you have images or video or music or just text, so not text plus numbers, but just text. For example, you want to do a translation from one language to another language, or like you want for images, you want to do image segmentation, something like that. For those types of data, you use neural networks, and you have to read some tutorials on how to use neural networks. You normally use PyTorch. I would recommend PyTorch, but you also can use TensorFlow. It's also really, really great. If you have tabular data, then you try gradient boosting. There are three main libraries in gradient boosting: XGBoost, CadBoost, and LightGBM, and you can try all three of them. Also, if you have, those are the simplest thing to try. You can also try random forest, linear regression, but the very first ones are these ones. It's like a very simple recipe.
Okay, that's great. So yeah, most of the people who are viewing these sessions are students, so they would like to know what, where can we apply these applications of CadBoost and what projects?
How they can apply, or where it is applied?
Where it is applied mostly, and where can we see it being applied?
Yeah, so it's applied in many different places. It's applied in Netflix. We know about that it's applied in Netflix for recommendation of content. It's applied in many places in Yandex. Yandex is biggest tech company in Russia. It makes self-driving cars, taxi, everything what Google does, plus everything that Netflix does, plus everything that Amazon does, all of that. And CatBoost is the core of all the products there. So search engine works on CatBoost, weather prediction works on CatBoost, recommendation systems work on CatBoost. So everything works on that. There is a bunch of other places where CatBoost is applied. For example, you might know JetBrains. They are you know JetBrains. So they are doing this they are suggesting when you are typing code, there is a suggest of what you are typing, and this suggest uses CatBoost. And yeah, so it's really used in many places. There is I know it exists service that is called Kareem, and they are using it to predict if there will be a lot of cars on the road or not. There is Cloudflare. I don't know if you know Cloudflare, but they are using CatBoost to make classification if someone is a bot or it's a real person. Basically, it is used everywhere where you have tabular data as an input. Like there is an example that described with a bunch of numbers. Then you use CatBoost.
Yeah, so it's like it can judge on like past data as well as real-time data. Like
so on
when
past
it
data,
has
you are training the model. So you get the past data, you store it somewhere like in a database, then you download it to your machine, and on past data, you train a model. And then starts the production. And you get this model, this file with a model, you put it into your service, and this service makes predictions for the data that it has never seen before.
Yeah.
So CatBoost is very production ready thing, because it's used like in ads and search engine and the recommendation systems. It needs to run very fast, and I told that it's like a very high speed thing. Because two other projects, XGBoost and LightGBM, they came from research projects, and this one, it came from production. So this one is exactly the one that you normally use for production purposes.
Yeah. And towards the end, you talked about hypertuning. So you said that when we have higher quality, we'll have lesser training time, and like when we have higher training time, we'll have a lesser quality. So it completely depends on the the preference of the user.
No, so if you train it normally, if you train something longer, and you set a smaller learning rate, you will get a better quality. It doesn't apply always, but it's normally like that, especially with gradient boosting. So if you are ready to train longer, then you set your learning rate to some small value, you set your number of trees to some big value, and you train long. And this will give you a slightly better, it might give you slightly better quality than the default one. Like in CatBoost, default is 1000 trees. you can set it to 2000 and you might get a little bit better quality. But it's not that huge of a difference. If you set the number of trees to 100, you will not get good quality. So 200 will be better than 100, 500 will be better than 200, and 1000 will be better than 500.
Okay. Yeah.
But then the difference starts getting smaller.
Yeah. Okay, so I guess we don't have any more questions. Yeah, that will be it for this.
Thank you
Yeah.
so much for listening.
Yeah. Thank you, Anna.
Okay.